And I believe all of you have studied for the quiz one. And so you people are familiar with the field expressions. That is how this electric field is induced by a point charge, and how it is acting force upon another charge, line charge, and many things actually we have discussed. So uh, and if you see very properly, all these field lines will be mostly excited out of the charge or charged body. So that is one reason that if you see the Gauss law directly, it will describe the behavior of the electric field. That is, it is always excited out of the particular structure, and most probably within the with respect to the local surface. If you take a particular local surface, and perpendicular to that you will find the electric flux, or even uh, the the electric field itself will be perpendicular to that. So that is why it is highly relevant with the charge q of the body. So that is what we have seen, and we have seen many problems out of that. And so today onwards, for the next sixth class, we are going to discuss about the magnetostatics. And for your cat 1, this module 1 and 2, that electrostatics and magnetostatics are going to come. So you can start to study along with this topics. Every topic actually you have to explore then and there. And so you have to read out the book as well. So magnetostatics actually, it is actually started very long back, but originally it is started well before the electrostatics. I already told about that. In fact, the very first invention of the magnet itself, the starting point of the magnetostatics. So it is available in very long back situation itself. But originally, when Hans Orist, when he developed the theories of electrostatics, he found out some interesting phenomena that when a current is passing through a wire, if we take a small thin wire and if it is carrying a current, then when he moved the compass nearby, so he found that actually the needle is keep on deflecting, and its orientation, this orientation of this needle also keep on changed. So that is a clear instinct that, because we already know about that, the magnetic needle always respond to magnetic field, not even to electric field. So, and this orientation very well changed in all the directions. So this clearly give that if there is a current flow which is completely made up of charges, uh, then there are supposed to be a magnetic field induced. And if a line is carrying only charges, there is no moment, then only magnetic field electric. Yeah, am I audible to you? So when we take line charge, and always the electric field alone be excited out, but whenever there is a current start to flow, the magnetic field is generated or excited out of that. So that is what originally been found in the time of Oersted. But along with that, Biot and Savart, they also developed the theories more mathematical manner. So that is how actually this magnetostatics were developed. And in Oersted book, we can very well see he has commented that how this magnetic field is deflected along with that, and whenever he changes the velocity of the charges, which means the current increases, he also found that it is directly proportional. So he has given the key point, and this clearly state that actually how this magnetostatics or the magnetic field and how it is relevant with the current passing through that. This was the very first workout being done. And later, Biot and Savart, they have developed the Biot-Savart's law. And here also they have given with more mathematical or precise, and they have done in the same year itself, they have done experimentally. So that is why actually we could see that in the case of Oersted, but Oersted actually he has developed more other theories, not only this magnetic field, and but in case of Biot-Savart law, it's more relevant with magnetic cases. And this magnetic field, so we can easily say one particular thing. Whenever a charge is stationary, it will produce the electric field. The moment it start to or go around, means if it is moving in a particular direction, which we call current, then the magnetic field immediately generates. And this is the same phenomena makes the magnet work. I believe most of you have studied about magnet, how it works. Can anyone say that how magnet works? Anybody who studied, uh, maybe I think in the 11th standard or 12th standard you have studied about this. Is it how magnet works? Can anybody tell about that? Mhm. There is a big silence. I think all of you have studied about that. Okay. So in case of any material, if you take that, it will be quantized by different quantum numbers. I believe all of you know about that. That if it is a particular atom means uh, that is described in the particular orbit, which cell and which orientation, in what direction it is spinning. So it is S is having two spins, so +1 or -1, like that. Actually, it will be clearly mentioned. So this is how we could say that in every orbit or in every particular state, there will be two electrons can be available and one will be rotating perpendicular to another. So like that. So this is the basic theory. But in some stable ionic states, let's say if you take iron and you just um, if you heat it for a very long time, or if it is uh, hammered or something, so whenever it is mechanically disturbed, then it loses one electron. Therefore only one electron alone will be there, which will be spinning in one particular direction. And whenever there is a change in the acceleration or the moment or particular velocity over the particular charged body, the magnetic field excited out. So that is how a spinning electron will be exerting its magnetic field perpendicular to uh, the the spin direction. In case of most of the materials, the atom will be having uh, two spins. So one will be having magnetic field and in this direction, another one will be having magnetic field in this direction. So they cancel each other ultimately. So there is no magnetic field in most of the materials, but in these type of magnetic materials, there will be one spin will be dominant, we can say, or in other words, only one spin alone will be there, and they group together. So if there are multiple charges nearby having magnetic field, these all magnetic fields. So each and every place we have magnetic field. These all magnetic fields together produce the exerted magnetic field. So that actually goes in a particular direction. So that, and if it is starting, then it has to close up. So it closes up in this particular direction like this. So we will see about this magnetic material maybe at the end of this unit. We will study as the magnetic material itself. At that time, we can see the types of magnetic, like ferromagnetic, ferrimagnetic. So like that, several properties are there. So this is actually the one interesting thing you're supposed to know about the a moving charge, or moving charge in a particular velocity, or revolving charge in a particular angular velocity. So that always produces the magnetic field. So this is actually mathematically described by Biot and Savart. And so both are actually work together, and they have come up with the idea of how this magnetic field is oriented, and how this vectorial representation can be done. And they have proved both mathematically as well as experimentally, and they will be very successful. So, and this is what we now refer as Biot-Savart law. But Maxwell mentioned this is the Gauss law of magnetostatic. So this is often referred as Gauss law of magnetostatics, like we have Gauss law for electrostatics. Similarly, this also considers Gauss law of magnetostatic. And then we have Ampere's law, in other words, to explain the similar behavior. So what we supposed to remember in this mathematical expression, that if we have a line vector, and let's say we have a line, and this is a wire which is carrying a current of I, and this, whenever it is carrying a current at a particular point, let's say at an instantaneous time, the current is flowing through this a small wire of length dl. Okay, so we already have seen that if there is a line charge which is having line charge density, and if we multiply with a small l, and this together we call this is a dq. So which we often refer, this is actually small charge element. Similarly, here also we have current density will be there. Okay, this current density here we are calling it as I, and that is passing through a small length, and I am going to multiply this 2. So this is generally referred as small current element. So hereafter, whenever I say small current element, immediately you have to think about this I into dl, where this dl is very, very low, such a way that the magnetic field, whichever is, let's say you take a small length, this length is having starting point and ending point, but with respect to the distant point R, this particular point P, the magnetic field induced from here to here both are same. So that is how we can simply state about this small length dl. So that is how it is defined. So it is called a small current element. Okay. Otherwise, if you multiply with I into dl, that is will be called as current element. But since it is a small dl, or the dl is very extremely small or infinitely small, then we can call them as a small current element. Now the question is how this small current element produce the magnetic field. So how to define that? So here we can see that there is a line, and in that line, this current I is passing, and at a particular point in this case, so we have taken a small length dl, and this dl is having its own vector. So that is nothing but the L vector itself. From that, actually, we will get the dl vector, and this I into dl will be a small current element. So that altogether we can consider as a vector 1. And this is because of this small current, there is a magnetic field produced. So that is a small magnetic field is produced at a distant point P. And so this particular point, you can see that it is given with a star mark. So this is actually defined like the current is actually going inward to this paper, or inward to the screen, what you are seeing here. So this is actually going inward direction in this side. Okay. So in other words, you can see here, so it is going in the inward direction. But whenever the current is going in the opposite direction, then you have to mark this is like a circle. So that is what is described here. So the current, whenever it is this mark is available, then it represents that the current is coming, or the magnetic field is, the vector is actually coming out. And whenever you have a cross with circle, and you will be, you can assume that is a current is actually heading towards the paper, or heading inside the paper like that. So here the current is actually going in the top side, and we can see that it is going inward to the paper or screen, uh, which we have the reference here. And so this dh can be mathematically described like this. So what is that is nothing but the dl and this r vector, both are actually supposed to be multiplied in such a way that we will be having this vertical to both this dl as well as r. So in other words, we can say that this dh vector will be perpendicular to both this dl vector and this r vector. So there is only one possibility, that when we take the cross product of this two, we will get this perpendicular vector. So that is how, in other words, we can say that whenever there is a current is flowing in a particular line vector, then just around that you will be having the magnetic field. Just the magnetic field will be just around it. So that is how we can describe the magnetic field, and it is the magnitude of the DH is given over here. So, and in general, we always add a constant proportionality constant, and this is very well experimentally proved that it is 1 by 4 pi. And so by substituting that, we will get the scalar form, which we can say that I into dl sine alpha, where alpha is the angle which is created by this uh, the line vector which is joining this point of the small current element to the point P with respect to the line vector itself. That is the angle created by that. So this sine alpha clearly indicate that whenever this alpha is 0, then there won't be any magnetic field. In other words, we can say that if you see there is a current is flowing in this direction, and you keep the point here P, and you measure the magnetic field, there is no magnetic field you can't, because it is just going around it. So you have to keep, most probably, from this along the line, you should not keep any point of reference for measuring the magnetic field. Just from this a particular distance, you have to keep somewhere else, here, 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 here. Then you can definitely get the magnetic field. So that is what this clearly indicate that. And here the vector form. So that clearly indicate that this small current element vector and this line joining vector, that is the corresponding AR vector. We have to take the cross product of that. So this cross product always will give another vector, and that vector will be perpendicular to both this DL vector as well as this AR vector. So why I am generalizing that instead of considering any coordinate system, because it is very much we supposed to see the perpendicular property between these two vectors. So this, whenever you keep it in a x-axis, y-axis, there comes the all the unit vectors will be popping up, and we can see some in examples. So we already know about this AR vector. AR vector is nothing but this R vector divided by the magnitude of the R. So when you substitute that, you will get this R cube will come instead of R square, and in the top you will get the R vector. So this is the most easiest form to define that. So this expression, when you compare with uh, the so-called Coulomb's law, so you will see very similar, except this epsilon naught, because here we are considering only the magnetic, and epsilon naught will not come. In future, we will see that the mu naught will come. So that will be done with some other reference. So this is the so-called Biot-Savart law. So the Biot-Savart law clearly tells about that whenever there is a line or a particular surface or a particular structure, whenever it is carrying a current in a particular direction, the current direction is very important here. So that is described by this vector. So this, whenever there is a current is traveling in a particular direction, just around that the magnetic field will be available. But the direction of the magnetic field will be perpendicular to the current, as well as the line joining of the point to the current vector itself. So that is very interesting property. Most likely you can easily say that the current will be just around that. But the question is how we can say it is heading towards the reference plane or heading out of the reference plane. So how to describe that? So for that, we can use this right hand rule. I think most of you have seen this right hand rule in the 11th or 12th standard book. And so we can easily take this right hand, and if you put the thumb up and close all the other fingers, so you will get this posture. So here it indicate this thumb actually tells about the direction of the current, and this all the fingers actually telling about this direction of the magnetic field. So you can very well see that how, so whenever you rotate this So whenever this current is going upward direction, then it is going like this direction. So that is what that. And whenever you put this thumb down, then it will go in the opposite direction. So by the way, so if you see this, if you take the cross section, then this particular point can be represented as like this. But here, this particular point can be represented by a point with the circle. So that is the only difference between this current going up and down direction. That how to do it whenever we do for a tricky structure, we're supposed to clearly know about this line vector. So what is this line vector? And what about the line joining? That is R vector. Both we have to take cross product. So L vector and R vector so you will get a resulting vector which will be perpendicular to both L vector and R vector. So that's supposed to be the vectorial direction of the magnetic field. So that is very, very easy. And as we can see that the magnetic field, they close each other uh, in a particular given point. So the force which is induced by that can be calculated by means of the another current which is passing through that. So when you multiply that, you will get the force very similar to that of the force between the two charges. So we can clearly see that there are two currents traveling in the same direction and they produce the magnetic field. So both the magnetic field will be just in the same direction. So they don't close each other, which in other words, we can say that they won't link each other, which in other often we say that the linkage is zero. Okay, so since the linkage is zero, these force actually they won't attract each other, they will repel each other. And in case of if the current is going in the opposite direction, so one will be going in this particular direction, the another one will be going the same direction. You can see that. So they close each other like this. So the magnetic linkage will be happening. So they tend to attract each other. So that is how the two magnets also linking each other and they attract each other. And you can see the physical movement also. So that is the interesting part. So that is how this mathematical expression can be explained. So this is Biot-Savart law. And in this Biot-Savart law, or in general, the magnetostatics, since the moment of charge is coming to the picture, we supposed to define the current in different forms. So whenever we have a line element, or whenever the current is passing in a line, the line, in other words, we can say that its width is zero. Okay, or it is infinitely small width like that. So such a way that we can't even measure it. So this small wire which is actually carrying a current, and that is represented by current density I. Okay, so this is we have to be very clear about this expression because this is the expression used in the textbook. Both the textbooks, they are keeping the same type of expression, and the current actually traveling through a small length. So the small current element will be given with I into dl. And this vector, of course, will come into the picture. And in case of surface current density, which is given by the factor K. So, and for a volume, J will be coming into the picture. So in most of the books, they will always mention the current density as the J, but here whenever we represent in terms of a line or a surface or a volume, so we're supposed to use these three different notations, I, J, K. So I, K, J, like that. Actually three different notations are followed. So you should be careful about it. And since we are actually, if you want to calculate for a line vector, we're supposed to integrate over a line. There is no closed integration. So we're supposed to be very careful about this. And then second thing is whenever there is a surface, we're supposed to integrate over the surface. So you're supposed to follow the proper vectorial forms. And in case of J also will be having its own vector. And in case of dV, it won't be having any direction, but the current J will be having that. So that's a minor difference because there is a 360 direction, any direction the current can flow. for the volume. So here the only difference is the current direction will be taken care by this J vector, while in case of the surface and volume, the line vector as well as surface vector will be there separately. And so this is how the we supposed to keep this in mind whenever we do the integration or whenever we calculate the magnetic field out of a particular structure. So the very first thing we have to do in any case, both the electrostatics and magnetostatics, once the structure is given, we have to tell what type of it is, whether it is a line or surface or volume. Then there will be most probably ready-made solutions will be there, so you can directly use it. Otherwise, you have to derive that using the using this laws, Biot-Savart law or Coulomb's law, whatever the given condition is. So let us try for a straight wire, which is a finite wire, and this wire actually has a total length, let's say L, and which is defined in the z-axis. Okay, so in this z-axis there is a wire, and this wire has starting point, and the end point is there, which is defined like A and B, very similar that of your the electrostatic conditions. The very important difference is there actually it is given with the charge density. Here it is given with current density I. Okay, so that is how it is. These are the two main difference, and then remaining you can see that the entire representation, everything quite same. I believe you can easily understand that. So this line we are actually going to keep in the z-axis, and along the x, this is a x, y, z, and this is we can consider as a we can even consider this as the y direction instead of this one. So this is the y-axis, and this is the origin point 0, 0, 0 point. So along this z-axis we have the line vector, and this line is also defined properly, and the star we are going to take a small dl, a small length we are going to take, and this small length is placed or it is located about height h from the origin point. So this particular point we can call it as 0, 0, h, and we are actually going to place this with respect to the origin point along the y-axis. We are keeping this point P where we have to calculate the magnetic field. So that is what our first objective. So this, of course, with respect to that, the magnetic field will be just go around this line vector. So we can see this way it is going around. So it is going towards the screen. Okay, that is how it is represented, and at the particular point P. So this point P is located at a radius of rho. So we are going to assume cylindrical coordinate system. So this can be represented as rho, 0, 0. So along the phi equal to 0 direction, or phi equal to 90 degree, or whatever it is. So we will assume like this. Okay, so in that case, this is supposed to be the x-axis. If it is equal to 0, if it is equal to 90 degree, then it will be y direction. So whatever it is, that's not a big deal. So we are going to consider this. Now, very first thing we supposed to do is we supposed to find this r vector. So this r vector is nothing but line joining of this dl with the P point. So it is starting from here and ending at point P. So the very straightforward answer is point this to this. So in other words, rho, 0, 0 minus 0, 0, h. So you will get rho a rho vector minus h a z vector, because along the z direction it is available. And what about the phi direction? There is no change. So obviously that particular term need not to come. So this is the r vector. So this is one of the very important vector, because the magnetic field is going to be perpendicular and the current also going to be perpendicular to that. So by this way, since the r vector is known, we can easily write the Biot-Savart law for the small current element. So here we have a small current element I into dl, and the r vector, we are taking the cross product of that divided by 4 pi r cube. So this is the simple Biot-Savart law. And here, what is this dl? Dl is nothing but a small current element along the all small length in the line along the z-axis. So we can easily define this dl vector is nothing but dz into az vector. So r vector is also known, r vector is known, and dl vector is known. First, we will take the cross product of them. So the cross product of this two, we can easily multiply them by simple, we can take term by term. So this is the first term, this dl vector into the rho component. And here also dl component with the z component is multiplied. So here we can, first thing we supposed to notice that whenever the cross product of same vector is coming, then obviously sign 0 will come, therefore you will get 0. So this entire term is going to be 0. So that is why we are getting this dl into r vector is nothing but rho dz a psi vector. A psi means a phi vector. So this clearly indicate that the magnetic field is going to be just around the current. So this is the d phi vector. And then we are actually going to substitute this all. So we already, and this r vector magnitude, we can easily say that it's nothing but rho square plus h square whole power 1 by 2. And we are substituting everything else here. So we will get I, this I is coming from here. This dl vector into dl vector into r vector will give rho d and dz. So this is coming here, and a phi has come from here, and 4 pi, and this rho square plus h square whole 3 by 2, because we are having cubic. So I believe all of you are clear with that. Any doubt you have, you can suddenly ask. There is no problem at all. Okay. So now we got the expression for current and for a dh, and in order to calculate for throughout the line here to here, then we have to take a integration. So whenever this integration, when we are doing over this, then obviously the position of the dl supposed to be considered, because this position supposed to go along the z-axis. So whenever we go along the z-axis, every time we supposed to calculate this rho vector, and all the time we have to suffer. So instead of that, the best method people used to follow is placing the angle. So what here it is being done, that this line vector, this dl vector or the line vector and this r vector both are going to make an angle of alpha. And now we can define alpha in terms of both this dl vector as well as r vector by making the triangle, and therefore we can define the edge points as alpha 1 and alpha 2. I believe you are already familiar with this similar representations. So this alpha will vary from alpha 1 to alpha 2 or alpha 2 to alpha 1, whatever it is. So depends on the position. If this particular point is here, point P is here, then this is very nearby. So obviously we will be changing the representations. But anyhow, so the point which is close to the origin point is A, and this is B, and correspondingly alpha 1 and alpha 2 is defined. So this is actually these kind of crucial things you're supposed to notice. Then only you can solve the problems also easily. So therefore, this position at any particular point in the line can be represented in terms of alpha. It is very easy that we know that this z is can be at any particular point, z can be represented by this triangle as rho cot alpha. Okay, you can take the tan and you can take inverse of that, then you will get the z, and this rho can be depleted. So you will get z is nothing but rho cot alpha. And we are going to take the differentiation because we supposed to put this dz. So this dz we are calculating, which is nothing but minus rho cosecant square alpha d alpha. So that is what we are actually going to substitute. Also, we supposed to find the limits of a and b. Therefore, when at point A, you will get alpha equal to alpha 1, and at particular point, alpha become alpha 2. That's all. So you are going to represent that here. So this minus symbol has come here, and I by 4 pi is a constant one. We can take it out. And this rho cosecant square, when you multiply with this rho, you will get rho square cosecant square, and dz supposed to become d alpha. I'm sorry for that. So d alpha. And then in the denominator, we are going to put the magnitude. So that magnitude you can easily calculate by means of calculating this total. So by the way, you can get this rho square plus h square as a simple trigonometry formula. When you work out, you will get rho square cosecant square will come. So by the way, you can put this here. So you will get rho cube. This cosecant cube alpha will come, and then this and this you can cancel, this and this you can cancel. You will get cosecant, and that you can bring it to the top with as a sign. Is there any doubt you have in this up to this step? Okay, so you know how this I has come 4 pi and rho, and why we take rho outside, because it is completely independent of alpha. And then I believe you have seen that how sine has come. So sine d alpha. So now we have to just integrate. We very well know that you will get cos. So you will get cos term will come, and so you will get cos alpha 1 minus cos alpha 2, like that is going to come. This minus symbol, when you multiply with that, you will get this is plus, this become minus. So by the way, you will get this expression. So this is a very, very simple. You can see that within one page itself, we have derived the expression for the magnetic field for a current carrying conductor of finite length L. So this length L in terms of alpha, it is defined. So that's a minor difference you should always see there. So the magnetic field is highly depends on the current I. So the current I increases, magnetic field strength will increase. And then this 4 pi rho. So the rho is nothing but the distance of the particular point, vectorial distance from the line. So that is also largely affecting the magnetic. At the same time, in what place it is located. So if it is going around somewhere else here, or if it is exactly placed perpendicular, so that is going to change the so-called the R vector. Therefore, that ultimately affected. So the alpha 2, alpha 1. So, and then this A5 vector clearly says that the with respect to the line, since it is along the z axis, so whenever there is a current is traveling along this wire, the current will go around that along the phi direction. Okay, so so this completely make a closed loop. So the magnetic field will be always be a closed loop. So that is what we're supposed to remember. And we can also have some special case that if this point A is at origin point like this, so we have this line. So the point A is here at 0, 0, 0, and point B is at infinite. So which we call semi-infinite. So this for a semi-infinite case, we have this A and B locations, and corresponding alpha 1 and alpha 2 will come like this. So cos 90 degree, you will get 0, and cos 0 degree, you will get 1. So there comes the magnitude of 1 itself will come. So that is nothing but I 4 pi 12 alpha. So this is the semi case. And if you take a infinite wire, then obviously we know that the here we think actually is there any possibility of cancellation will come, because there won't be any, because simply current is flowing just around that. So even if you take infinite also, the same behavior is going to come. And when you put both the cases, one will become 180, another will become, so both are going to give the same value. So you will get 2 times, 2 will come. Okay, then you will get cancelled with this 4, you will get this I 2 pi rho A phi vector. So this is the magnetic field for a infinite line. And this expression, I believe that it is very, very same as that of the same thing for a electric field. So electric field for a infinite is nothing but this charge density of that divided by 2 pi epsilon naught rho into a this an vector, which is normal to the wire. So that is the main difference between this electric and magnetic fields from a line vector. Okay, so that is what you could easily get out of this. Have any doubt in this? So you just always daily basis, you just once again you just study and you close the book and you can solve and all these step by step without missing out with the proper notations and proper statements. All these how this is calculated, what is this, all these things you have to also supposed to write, and it's supposed to be a mathematically decent way to reach this. Okay. So I think this derivation is available in multiple web pages. There also you can refer. So we got the magnetic field for a finite line, for an infinite line, for a semi-infinite and infinite lines. We have the data. So we got the magnetic field. Now the question is, since it is along the z-axis, we can clearly say that it is along the a5 direction. But if it is available in different directions, let's say this is x y z axis, current is going in this direction. Let's say x y z direction it is traveling. Then how to do that? So if we supposed to take the particular point P and draw the r vector. The r vector is going to be perpendicular to this vector. So this is a line vector. Both when you multiply, you will get the corresponding normal vector, which is nothing but L vector cross R vector. So you will get, let's say you will get something like M vector. And this M vector, if you divide by the magnitude of the M, then you will get the normal vector. So that is what's supposed to be the A5 vector correspondence. So we will see when we work out on multiple examples, we will understand that. So here is one of the very famous example. You can see that it is solved. You can see it in some of the YouTubes also. This particular problem is solved. And there is a triangle current loop is placed along the X and Y axis. Okay, so along the X and Y axis, so you can draw like this. So this is actually X, Y, and this is Z axis. So so like this it is placed. Okay, so now we have to calculate the magnetic field at a particular point P. And it is carrying a current of I, that is 10 amps. So that is given. And we have to calculate the magnetic field at the point 0, 0, 5. So how to do that? So that particular point, it is here, 0, 0, 5. So, and we have to calculate with respect to the side 1. So this is the side 1. So this is the side 1, side 2, side 3, like that. So it is very simple that it is along the x-axis. We supposed to be very we have the expression along the z-axis. If the current is traveling along the z-axis, the magnetic field is around this. So we can easily find out. But now it is simply changed along that. So magnetic field will be just in this direction it's supposed to go. Is it? So then how we can calculate at the particular point P. So how it is going to be here in this particular point. So that is what we are going to find. So let us see here. So this is the point P. So along this X and Y and Z axis, the current is the current line is placed and the current I is passing. So it is passing from A to B, where A is located at 0, 0, 0. Okay. And then B is at a particular point, and which is nothing but 2, 0, 0. So in this here it is clearly mentioned where it is. Okay, so now we have point A and point B, both are available, and the magnetic field will be just, it will be going. So you just draw the simple thumb rule like this. So this is thumb and this is all other fingers. So you can easily find out in which direction the magnetic field will be available. So that, okay. So next, now the unit vector here it is AX vector. So you will be getting this I vector is nothing. So this I vector is going to be 10 AX vector. So that is nothing but the current which is passing through that. So you can easily map here. So the alpha 1 is will be calculated with respect to A, and the alpha 2 will be calculated with respect to B. So therefore we have to calculate this cos, and so this problem can be directly represented here. So you have to calculate this cos. I is known, and rho is nothing but the particular point at 0, 0, 5. So which is exactly located at rho equal to 5. So then you have the value of rho, and we're supposed to calculate alpha 2, alpha 1. So alpha 2, you can easily say that it is going to be 90 degree. Therefore, cos alpha 1 will become 0. What about cos alpha 2? So cos alpha 2, you can make it as a simple triangle, and this value is 2. Okay, so this opposite side is 2. Sorry, this is actually adjacent side is 2, and this opposite side is 5. So therefore, we can easily calculate the cos. So the cos will be nothing but adjacent side divided by the hypotenuse. So by the way, you will get this 2 divided by root of this 5 square plus 2 square, which is nothing but the length of this r vector. So that is what we got. And so this is the cos 2. So we are going to simply substitute everywhere, and you will get the magnitude. The magnitude is very simple part. You can easily calculate. But what about this unit vector? So how to calculate the unit vector? We already know that the current, whenever it is traveling along the, let's say along the x-axis, then the current will go in this way. And whenever it is going in the opposite direction, it will come in the opposite direction, just opposite to this direction it will come. Okay, that is the key thing you're supposed to remember in this case here. So at this particular point, when actually, when the magnetic field is passing through here, then at this particular point, it will take only one direction. Okay, that is along the direction which is perpendicular to both this x-axis and the z-axis, which is nothing but the y-axis. So the current will pass only through the magnetic field will go only along the y-axis, and that is a special case only at this particular point 0, 0, something like h. Only it will pass through that. But what about here, somewhere else? It will be having different vectors. So this A5 vector supposed to be AY vector, and the question how this negative term will come. So automatically negative term is coming from this cos itself. We need not to worry about that. But what is this indicate? That the magnetic field is just opposite to the y direction. Okay. So in order to understand that, let me draw this. So this is the x, y, z axis, and the current is in this direction, and it is flowing in this direction. So you can draw the thumb rule. You draw the thumb, other fingers. So magnetic field will be just like this. It will go, and you can see that this is actually the direction of y vector, and this is the direction of minus y vector or ay vector. So that is what gives this meaning for negative. Okay, so that is what you have to keep in mind. I believe you have got the idea. Is there any question or something? So for now, no people is asking question about this numerical problems or anything. So let me evaluate the quiz. I will understand how far you have listened to the class. I believe you got it. So we can also do for the same problem for this side 2 and side 3. I think there is some workout being done for side 2, I think, and the answer is available in book itself. Let us see how to work for side 3. So in case of side 3, which is actually which is placed both along the x and y direction respectively. So we're supposed to be a little careful about this problem. So this is actually the x-axis. So this is the y-axis here, see here. And this is the line which is traveling. And it is available at this particular point 1, 1, 0. It is available on the xy plane. So that is this particular point. So A is this point and B is this point. So now we supposed to calculate the angles. So this angles are nothing but alpha 1 and this is alpha 2. So how to calculate the alpha 2? You're supposed to calculate this triangle, and by the way, you can easily calculate that. So that is very simple process. And so here we know the current. And what about rho? Rho is again going to be 5 only. And the alpha 1 is going to be 0. Therefore, this entire term will become, this particular term is going to be 0. And what about this cos alpha 2? You have to calculate this hypotenuse and the adjacent side. Okay, so this is the adjacent side, which is going to be root of 1 square plus 1 square. This is going to be root 2, and this value is going to be root of 5 square plus root 2 square, which is 2. So you will get 27. Yes. So you will get this. So this is anything but cos. So when you substitute, everything will come. The question is all about this direction of the direction of the magnetic field, which how to define this unit vector. Okay, we supposed to remember that the unit vector supposed to be perpendicular to both the line vector at the same time to the line joining vector. Okay, the line joining vector from here to here. Okay, so this line joining vector, both it's supposed to be perpendicular. So the nearest point in this line is this vector, which is nothing but AZ vector. So we need to find the unit vector which is perpendicular to this line vector as well as this vector. So that is the corresponding one, which we call as A5 vector. So this A5 vector is nothing but, okay, we have this vector, we know that it is going to be magnitude of 1 and 1. So that this L vector is nothing but 1 AX vector plus 1 AY vector plus 0. So that is nothing but this L vector. And this L vector's unit vector is going to be AX vector plus AY vector divided by root 2. Okay, so that is nothing but the unit vector. Now we have to take the cross product with the AZ vector. So if you take the cross product of that, this both the vector will be having only one cross product, that is going to be minus of that. Okay, exactly minus of that will be the perpendicular vector. Therefore, only they will finally get the corresponding. So that is why you will get this AY vector is going to be just negative of that. Otherwise, there is no other chance. So in other words, the line which is along this particular direction is going to be the perpendicular to the both these vectors. So that is the corresponding thing. I believe so. It is correct or not? Can anyone? I think one will become plus. I think any one of them, either this plus or minus, because in this direction only you will be perpendicular to both this line as well as this vector. I think we can take any one plus. So along the we can take this as plus. So this is going to be the AY vector. A5 vector. And when you substitute that, you will get everything. Let me see. Yeah, here it is. So we will place this plus here. So plus here. So we are going to simply substitute everything. Then we will get this. So are you good with this vectorial representations and so on? So because the numerical problem, what we are actually going to ask in the exam will be very similar to that. So you're supposed to be very clear about that. Solve as much as problems in the book, in both the books, both H as well as the Sadiq, and